you know, sunset, the moon is in the east, and you'll watch it come across, then it'll be on the horizon again if you stay up all night before dawn. So it'll be over in the west, also on the horizon, look bigger there. What was Galileo's theory? His theory was atmospheric refraction. Which is the idea that the atmosphere magnifies the size of the moon, and it had to do with something about the shape of the geometry of the atmosphere, and you'll even find this in some physics textbooks in the chapter on optics, because they haven't gotten word yet that this theory is wrong. Of course, we like Galileo's theory about the solar system better than we do Ptolemy's, although Galileo still didn't have the ellipse that waited for Kepler and waits for Newton in order to explain why you got an ellipse. Elliptical orbit. Galileo still had, you know, circular motions as opposed to elliptical orbits. But we like his theory at least that the Earth is going around the Sun better than the theory that the Sun is going around the Earth, which is apparently believed by 25% of Americans, the ones that are electing our Congress. I mentioned last time. So Galileo's theory is wrong. And you can disprove it, and in fact it was already disproved by Ptolemy, who looked through a tube and saw that the image size was the same. And he was able to use a very simple method. He had a tube with a sawtooth, and he could measure the size of the image. You look through the tube, you don't see any illusion. So the illusion goes away if you look through a tube and you just see the image of the moon. It isn't the image that's bigger. No, it's psychological. And so here's a case where we like the older theory, the guy who thought that the Earth did stand still and the stars and the moon and the sun and everything went around the Earth. So we don't like Ptolemy's theory. I mean, he was a very reasonable guy for the time. He thought about Aristarchus's idea that the sun was at the center, and he said, where's the wind? And, you know, if you throw something up, shouldn't it fall to the west? And he didn't know our current theories of physics. So he still had some wrong ideas, you know, about 1,800 years ago. Which fits the theory, fits the data better? Well, Ptolemy's, because you can take a photograph of the moon on the horizon and a photograph of the moon overhead, and the photographs come close pretty well to matching almost perfectly. You're actually about 4,000 miles farther away from the moon when we're looking at it on the horizon than when you're looking at it overhead, but that 4,000 miles compared to 238,000 miles is no big deal. And furthermore, it goes in the wrong direction to explain the illusion. So Galileo's theory is wrong, and if you find it in a physics textbook, go tell your instructor to write to the author of that textbook. They've pretty well gotten it out of most of the textbooks. Some textbooks have a lot of errors. Muller-Lyer illusion is one. You measured that for homework that you turned in today. The Muller-Lyer illusion is one that a lot of intro psych textbooks have actually faked it. I don't think they're trying to cheat, but sometimes people don't notice when they're cheating. I think what happens is, you know, the author of the book draws a picture and says to the artist, I want you to do a better job of this than I did. And the artist says, okay, you got a long line here and a short line here, and now we're going to, they draw what they see, a long line and a short line. And then the author sees it, come back and say, oh, it looks a lot better now that the artist drew it up. You know, my rough, they measured it out, maybe Khaled measured it out. Now Khaled, you know, I haven't seen an error in his text yet. It's one of the reasons he's got a better textbook than some of them. But I read an article about 10 years ago that 65% of intro psych books, the line that looks longer actually was drawn longer in the book. So as if it had been faked. So this line looks longer than that line. Yeah, it looks longer, it actually is longer. So you should always be a bit skeptical and check it. Go ahead and be skeptical and open-minded. Go measure it. Make sure it's actually an illusion you're looking at. All right, so that's Galileo. What? Ptolemy. Which one fits better? I'll go over Ptolemy's theory in just a bit. And what's the proximal and distal stimulus in the Ames room? Well, the distal stimulus is what's actually out there. So that's the physical size of Zimbardo. He's pretty tall. I don't know. How tall would you say he is? About 6'2"? What? Maybe like Kyle's height. Maybe a little taller. He's a pretty tall guy. So 6'2", that's physical size. That's how you'd measure them. That's what's actually out there. That's the actual thing that's out there. And what's the proximal size? Well, that's the retinal image. So the only way you know how big he is by means of this, what's on the back of the retina here. So the retinal image, that's equal to the proximal stimulus. So that's what you have. This one's the distal out here. The actual physical object that you're trying to judge. The proximal stimulus is the stimulus the person can use, because you people aren't touching me or measuring me, have devices on you, but you could estimate my height from where you're sitting by sight, by vision. And the only clue you have through your vision right now is the retinal image. So the size of the retinal image is your measure, but that changes. So one of the puzzles of constancy is, how is it when the distal stimulus stays constant, but the proximal stimulus changes? The person sees the object, and so what goes on up here, this is perception, S. Why is it that S stays constant when phi stays constant, even though R is changing? So that's another way to describe constancy. All right, perceptual constancy is that S stays constant when phi sub S stays constant, even though R changes. All right, here's the assignments coming up before I cover this stuff up. Let me start up the engine here. Due Tuesday, you can see what